All right, hello all 6 of you. Welcome back to Comp 3430. I hope that everyone's doing okay working on their assignments right now. I'm assuming, I hope everyone's doing okay. I'm feeling pretty tired. I didn't have a great sleep last night, but then, I mean, everyone I think is probably in the same boat right now, so yeah. I heard that the lineup for the Winnipeg Folk Festival is out. I don't know if any of you have been to the Folk Fest before, but it's a good time. One of the bands that's playing is called the Budos Band. I don't even know how to like classify their music or what genre you'd put them into. It's instrumental, it's good. It's kind of different than the usual music I listen to, but I think I'm probably going to go check it out. And plus, it's just got me thinking about summertime, especially when it's really cold. Again today. So what I want to do today, and what I want you to be able to do by the end of today's lecture, is I want us to look again at that deadlock code, and I want to spend a little bit of time looking at the solutions that I described at the end of last class. I want to clarify, in particular, the use of sorting our accounts to try and make sure that we can't have deadlock happening anymore. I don't want to dwell too much on this because I think that we've got the main idea of what to do with deadlock, but the sorting of the accounts was kind of this oddball. It doesn't really make sense that it works, or it doesn't make sense why it would work. So I want to take just a little bit of time to take a look at that today. And then after that, what I want to do is I want to write some code, and I want to look at some code that's going to use condition variables in a program. So the software that we've been working with, the code that we've been working with in terms of pthreads right now is pretty much limited to using pthread mutex lock. And the semantics of that are that when a thread of execution gets to the lock statement, it will block until the lock is available. Condition variables work with locks. They have locks as part of what they're doing. They enforce mutual exclusion, but the difference is that we can have a thread effectively go to sleep until an event happens. So not when a lock becomes available, but when it's told that something is available for it to work on. So I want to take a look at 2 examples for that. The first thing I want to do, like I said, is take a quick look at this deadlock.c file. Oh, but you know what? Before we do that, I want to take a look at what we're doing next week, because it's Friday today. So I've got the course webpage open right now, and I'm going to take a quick look at week 9, which is what we're looking at next week. One of the things that we've been doing so far with, well, everything, like in terms of processes and in terms of threads, is we see that these things are running concurrently. We can see that they're running giant air quotes at the same time, or in the case of multiple processors, literally at the same time. And as far as we're concerned, the operating system is switching around rapidly between these processes to make it look like they're all doing something at the same time. How the operating system makes that choice up until now has very much just been, it's an arbitrary decision, and whichever one is there happens to go next. But the operating system is actually making an informed decision about which process is going to go next. And this is the entire topic of scheduling. Scheduling is very much queues. It's queues all the way down. We're looking at threads and locks. They're ultimately implementing queues. We're looking at condition variables today. It's doing queue stuff. We're going to be looking at scheduling next week. It's more queues. It's queues. It's queues. It's queues. It's queues. In fact, there's a data structure that we're going to look at that's part of one of the scheduling policies that is a list of queues. It's queues everywhere. The readings that I've got for you are, there's 3 chapters here. They're actually fairly short in terms of the content and compared to the other ones because there's not a ton of code listings in these. The last chapter here, scheduling proportional share, this is chapter 9. I only want you to read the first few sections of this, and then 9.8 is the summary section. The sections 9.6 and 9.7 describe scheduling policy in the Linux kernel. So this is a real, actual scheduling policy, but it uses a data structure that's called a red-black tree, And unless you have taken Comp 3170, I don't think you've seen red-black trees before. You might have seen AVL trees in 2140. You might have seen AVL trees in 2140, yeah? Can you repeat that? In 3170, okay. So in either of those classes, you may have seen AVL trees, and they're related to red-black trees. It's a balanced data structure. But in that it's a learning outcome that's attached to Comp 3170, I decided that it doesn't really make sense because that's not a prerequisite for this course. So you're welcome to read about the completely fair scheduler in 9.6 and 9.7, but you're not obligated to read that. That's not going to be something that's part of our course. So that's next week, and I'm looking forward to that because it kind of illuminates some of the choices that our operating system is making about how to make these different processes run concurrently. So with that, let's take a look at deadlock.c. And like I said, the things that I want to do right now is really try to take a look at this sort accounts option. The file scope lock, that one I think is straightforward. We add a file scope lock and then we serialize all transfers between different accounts. The sort accounts option is going to be something that's it's different. It's a little bit unusual, but it's going to make things a little bit more complicated. So I'm going to pop over here to my terminal. I'm going to make this just a little bit bigger, and I'm going to open up deadlock.c here. And what I want to do here is I'm going to go straight to our deposit function. In the deposit function, what I want to start thinking about here is how to get these two accounts in a specific order so that, and the goal of this really is, sorting them is going to allow me to have total ordering of the locks. I'm always going to guarantee that the account that has the lower value or the lower identifier will get locked first. It's always going to get locked first. That's my goal with sorting these accounts. So I'm going to do this. I want to go up here and I'm going to add two new properties to this. I'm going to say bank account pointer from and to. So I want to declare these as file scope, as function scope variables. So I want these to be thread local. And then what I'm going to do here is I'm going to say if args from is less than args to, then I'm going to put from in this from variable. And 2 is equal to args2. So I'm just going to take the order that they were passed to me, and that's the order that I'm going to do it in. Otherwise, what I want to do is I want to say that from is equal to args2. I want to invert the order. So I'm reversing them here. And I'm going to also have an amount. And in the conditional statement, what I'm going to say is, if I'm not sorting them, then the amount is just equal to args amount. If I am inverting them, I'm going to say amount is equal to negative args amount. So by putting them in this opposite order, by making sure that the order of operations here is going to be always going to be from the account that has the lowest address first in this case, I'm effectively accomplishing total order on these locks. And total order, if you remember from our textbook, was this idea that we will always acquire the locks in exactly the same order. Every thread of execution that enters this critical section will try to acquire the locks in exactly the same order. By doing this, we're enforcing total order. So sort our accounts based on their address in memory. And this is us taking advantage of this idea that these are unique addresses for the accounts. In practice, I probably want to add an account identifier to the structure and then sort on that as opposed to the address. But sort our accounts based on their address in memory. to enforce total ordering of lock acquisition in the deposit function. So in this way, no matter what order they get passed in, we're going to sort them. We'll invert them in some cases and not invert them in others, but we're always going to make sure that we acquire the account that has the lowest address first in terms of the lock, the order of acquisitions here. I'm going to ask all 6 of you one question now. The next point here would be, I want to make sure that this works. And the way that I tested this last class and was eventually able to show that deadlock happened was that I just kept running it over and over and over again. And my question for you, and you can just do thumbs up, thumbs down, if I just keep running this over and over and over again, will I be able to show that deadlock can't happen? I said thumbs down, not shake your heads. Yeah, thumbs down. Okay, yeah. So thumbs down is thumbs down. I can't just keep running this because this is a situation where I just have to run it forever to show that deadlock can't happen. But I can go through and say, because of this total ordering of lock acquisition, that deadlock cannot happen. I've broken one of the conditions for deadlock, which is that circular wait. I've forced total ordering to happen, so there's never going to be a situation where there's 2 threads of execution waiting for each other to give up one of the locks that they're holding. All right. Are there any questions about that before we keep on trucking on to condition variables? All right. Okay. So let's go take a look at condition variables here. There's 2 things that I want to do with this. The first one is I want to write some code, and this code is fully contrived. The only reason that I want to write this code is to demonstrate the use of condition variables. I'm going to make some threads. The threads will do nothing, but they will wait for a condition, and then they will exit. That's all they're going to do. I don't want them to actually accomplish anything. I just want to use condition variables in a program. The other thing that I want to do is I want to look at some code, and I want to run some code that will use an actual use case of condition variables. So the code that we're actually going to look at is an implementation of a design pattern. So if you're taking Comp 3350 right now, or if you have taken it before, you may have talked about design patterns. I don't know where you're at in your course right now. Have you done design patterns yet? No, okay, so eventually you'll do design patterns. Design patterns are kind of like, hey, here's a general structure of a solution to this problem, but there's no code. This is just the structure of the thing that you might have. So an adapter is a kind of design pattern, for example, where you take the output from one function and you transform that object state into your own internal structure state. Like singletons, yes. Singletons is another one. So you might have seen those in Comp 2150 when you were taking that course. Oh, okay. The design pattern that we're going to look at here is a design pattern that's called a resource pool. The resource that we're going to be looking at here is threads. It's a thread pool, but a resource pool is another common design pattern that's used in places like web applications for databases. And the idea with this design pattern is that making these resources or acquiring these resources can be an expensive operation. So connecting to a database is an expensive operation. So instead of constantly connecting for every request that's made to the web server, you just open a connection and then reuse that connection over and over and over again. A thread pool it's expensive to cause threads to start up, so start a bunch of threads up and then just keep reusing them for work over and over and over again, rather than starting a new one every time you want to start something. So let's pop over to my terminal, and what I want to do first is I want to start writing this contrived example. The code that I've got here, I've already started working on this in this thread management repository. So if you've got this repository on your system right now and you want to have a bigger copy of it in front of your own screen, then please pull the repository. The code that we're going to look at to start here is this file right here. It's called conditionvariables.c. This code does a few different things that we haven't seen already, and so I do want to talk just a little bit about what it's doing. It's not directly related to condition variables, but it makes something slightly different than what we'd had before. The first thing that's different that I'm going to call out here is this. On line 7, there's this new header that I've imported here called stdatomic.h. When you're reading about lock implementations, atomicity is a very important concept. The atomicity here with locks is around, I need to have compare and swap. I need to have test and set. I need to be able to do two things in one atomic unit of an operation. This library gives you C functions that do those things. So in the code and the textbook, there's code listings of compare and swap and test and set. stdatomic literally has functions compare and swap and test and set. These can be used to build locks. These primitives can be used to build locks, but it also gives us access to new types. So on line 12 here, we have been using uint whatever underscore t to represent different unsigned integer types. The stdatomic library gives us access to a new type that's called atomic underscore uint. This is an unsigned integer variable. It's not specified how big it is, but it's an unsigned integer variable, and it has this atomic attribute. And so what that means is when I do things like plus plus on this variable, it's an atomic operation. It's not going to be a multi-step operation. It's an atomic operation, which is convenient for us because it's going to help us with what I want to accomplish with this code. The other thing that's a little different is starting on line 5 here, where I've included this syscall header. What we've talked about briefly with Linux is that we've got processes, and processes have IDs, and we have threads. Threads also have IDs. And when we were talking about that clone system call and this struct task struct, it turns out that they're the same structure that's used underneath. Linux also has this system call that we can make that's called getTID that says get thread ID. Please give me the thread ID for the currently executing thread of execution. But unlike getPID, there is no C library wrapper for that. And so we have to make the system call ourselves. We have to manually make the system call. And we can use the syscall function and specify the system call number that we want to make. So sysgetTID is a number. I don't know what number it is, but it's a number that says this is a system call that I want to make. And the syscall function will actually invoke that system call on our behalf. I want to be able to do that because I want to print out the thread IDs for each of the threads that I'm actually launching in this entire process. I want to see what their IDs are, because if I just call getPID on these things, it's always going to be the same value, and I want to see that they're different for each of the things that we've got. After that, everything else looks pretty similar to what we've had before. I'm calling pthread create, and I'm calling pthread join in a loop. I'm launching 10 threads. They print out their IDs and exit at this point. So what I want to accomplish with this code is I want to use condition variables. The setup that I've got here is I want to have my main process launch the threads, and then I want the threads to wait until they are told to start doing something, until they're told to start operating on some data, until they're told, in this case, to exit. That's the only thing that I want to do. So I want all my threads to start up. I want them to get to a state where they are blocked, and then when I send the signal, they should exit after that. So my process here is going to be, I want to start in my thread function. The first thing I'm going to do is I want to start working on using the condition variable that I've got. Condition variables, when we're operating with them, they must have a lock attached to them. There's a lock that has to be associated with the condition variable itself. So whenever you're using a condition variable, you'll always have a lock to go along beside it. The first thing that we have to do is we have to acquire the lock. We have to acquire the lock before we try to wait on the condition variable. So that looks the same as what we had before. So I'm going to say pthread mutex lock, and what I'm going to lock on is cv underscore lock here. I want to acquire this condition variable lock. Then what I want to do is I want to wait for a signal to be sent that says I can proceed. And the way that I'm going to do that is I'm going to call pthread underscore cond underscore wait. What I'm going to wait on is the condition variable itself. So this is the CV that I've created there at the top. And I also have to pass to this, and I'm going to just pop open another terminal here, and I'm going to say man pthread cond wait. There's two arguments that I have to send to pthread cond wait. The first one is the condition variable, and the other one is the mutex that I have locked. So I'm going to pass that address. And the semantics of this are that my thread is going to go to sleep, and it's going to release the lock. It will suspend itself, it will wait around, it will block until the condition is met, release the lock while you're suspended. So while you're blocked or while you're suspended, while you're blocked, you will release the lock. That means that any thread of execution that gets to this point will block. It's going to get stuck here. Once it gets stuck, it releases the lock so that other threads of execution can then also enter this section and also wait on it. We want to allow multiple threads of execution to wait around on this statement. So I'm going to sit here and wait, and then what I'm going to do is, once I end waiting, I'm going to say printf received signal acquired lock, and I'm going to print out my thread ID again. On line 32, this line is only going to get run once the signal is sent to us by somebody else. The only way that we get unblocked from line 28 on this pthread cond wait is somebody else sends a signal to us. Once we start executing after that line, so on line 32, the semantics of this are that we have the lock again. So order of operations here is acquire the lock, block, and then release the lock. And then as soon as you unblock, you have the lock again. You've got the lock. You hold that lock again. So once we're done that, then I have to say pthread mutex unlock. CV lock. I have to explicitly release it because I hold it after I have been allowed to proceed execution after that. The last thing I'm going to say here is that I'm finished my thread, and I will allow this function to exit to say that the thread is finished now. If I run this code, it's probably not going to work because I have not initialized the variable. I'm going to say make condition variables here explicitly. Make condition variables. Unknown escape sequence %\d. I'm bad at typing today. Make condition variables. Okay, this code isn't going to work because I haven't initialized my condition variable. I need to do the initialization of my condition variable in the main function. So I'm going to go back to my code, and I'm going to go down to the bottom here. And I'm going to initialize my condition variable before I start creating any threads, because I want to make sure that the condition variable has been initialized before they start trying to wait on that condition variable. So I'm going to say pthread const init. So this is going to initialize my condition variable. I'm going to pass it CV, and the other thing that we can pass to pthread const init, similar to when we're initializing mutex, is some attributes, but we're just going to ignore that those attributes exist and just say null for now. I don't really care what those things are. So I'm going to write null, and at this point, my condition variable has been initialized. I want my main thread of execution to wait until all of the threads have initialized themselves. So I want them all to start up, and then I want to start doing stuff in my main thread of execution. So I'm going to add something here. I'm going to say while threads ready is less than num threads. Num threads is defined in this main function here, and threads ready is that file scope atomic variable that I declared up at the beginning. And I'm just going to spin. So spin or block until all threads have reported themselves as ready. So they've all started up. We've started running code inside that threads function. I'm going to go back up to my thread function here, and I'm going to add, just after I enter this function, threads ready plus plus. I'm going to go back down here to my main function. I'm blocking it here until all the threads are ready. And then once the threads are ready, I'm going to send signals to them one by one to say it's OK for you to finish up. You're allowed to exit now. So I'm going to say this. While threads ready is greater than 0, printf, press enter to send a signal. Get char. So I just want to get enter. Just want to block until hit enter. And then once I hit enter, I want to send the signal to say that you should terminate now. The way that we send signals is to use this function right here, pthread const signal. This is saying I'd like anyone that's currently waiting on this to wake up and start doing something. They're allowed to enter that critical section. Before I'm allowed to send the signal, I have to acquire the lock on the condition variable. So I'm going to say pthread mutex lock. I want to pass CV lock here. I'm going to say pthread const signal, send the actual signal on the condition variable. So wake up anybody that's waiting, wake up exactly one thing that's waiting right now. And then I want to unlock this thing. So I'm going to quit that. I'm going to zoom into this, and I'm going to split in Vim. So my main thread of execution is currently executing in the main function. We called pthread create. We started up a bunch of threads of execution, and they're all doing work in this work function. My main thread of execution is sitting around here waiting for all these threads to say, hey, I'm ready now, by increasing threads ready. Each thread of execution will acquire this lock. Then they will get blocked. They will get stuck waiting for this signal, and they will unlock the lock. Once all the threads have reported themselves ready, my main thread of execution here is going to take over, and it's going to print out this message, wait for us to press enter. Then it will acquire the lock. It will send the signal, and then it will unlock the lock. By sending the signal, what that says is anybody currently waiting here, one of you will be woken up. exactly one of you. It doesn't matter how many there are, just one is going to get woken up. It will be allowed to do whatever it needs while it holds the lock, and then we'll unlock the lock at the end here. So I'm going to quit Vim on one side here. I'm going to zoom out. I'm going to make this again, and I'm going to run it. The state that we're in right now is that all of our threads have started. We only started 10 of them, so it happens quite fast. There's not a lot to wait for in terms of starting up one of these threads. And all of our threads of execution that are not the main thread of execution are stuck here on line 31. They are all waiting. They're all blocked. Our main thread of execution is currently right here on line 64. It's waiting for us to hit enter on the keyboard. So I'm going to press enter on the keyboard. Our thread is going to get unblocked because the main thread of execution will lock the lock, send the signal, and then unlock the lock. I'm going to hit enter here. And now one of these threads, the first one that got launched here, acquired the lock. It was woken up from the blocked state. It acquired the lock, it ended, and now our main thread has taken over again, and it's waiting for us to press enter. Made a mistake in this pro code, so I'm going to hit enter like 10 times, and then it's going to not do anything because I haven't decremented the number of threads that are currently running. So I'm going to come back up here, and I'm going to say threads ready minus minus. And then I'm going to hit Control C, I'll make this again, and then I'll run it one more time, and then I'll hit enter 10 times, and then it will finish this time. Okay, so good, yes. This is not exciting code. This is really not exciting code, but what it shows us is that we've got these threads of execution, and unlike pthread mutex lock, which is you either immediately enter the critical section and are allowed to complete, or you get blocked waiting until the lock is available, now we're blocking until an event happens. And the event is something that comes from outside. Somebody's going to say, hey, this thing is ready for you to work on now. So now you should wake up, do the thing that you need to do, and then either go back to sleep on the condition variable or finish, exit the thread that you've got. The other option that we have for this, so this is kind of this mechanical or manual, like wake up exactly one thread that's waiting on this condition variable. The other option that we have is to call pthread cond broadcast. Pthread cond broadcast will wake up all of the threads that are waiting. They'll each get to take a turn holding the lock and unlocking the lock, but they all get woken up instead of just one at a time, the way that we're doing this pthread cond signal. So pthread cond signal here is wake up exactly one thread that's waiting. And then I'm going to comment out this entire block. The other option that we have is I'm going to acquire the lock, pthread mutex lock. I'm going to unlock the lock. And then inside here, I'm going to say pthread cond broadcast. And I want to send this on the condition variable that I've got. Pthread cond broadcast says wake up all waiting threads. They don't all enter the critical section. So to be clear, they don't all immediately start operating inside that function. Pthread broad cond, I can't even say it. Pthread cond broadcast will go through all of the threads that are currently waiting on this condition variable and wake them up. In the same way that our loop went through and woke up all the threads, this is just one call that does that. I'm going to make this one last time, and I'm going to run it. Actually, I'm going to add a get char here, printf, press enter to end all threads, or to send signal. Get char. I'm going to make it one last time, and I'm going to run it. All our threads are going to start up. They will all be sitting at this condition variable waiting right now. And my main thread is taken back over, and I'm going to hit enter on my keyboard. And this time, all of them will get the signal. They all get it one at a time. Again, they are not all entering this critical section, because what we've got is that after pthread_conn returns, after we unblock from this, we have the lock. Only one thread of execution will be in here at a time, even if they all eventually get woken up by doing this. So the key takeaways here are, when we have a thread of execution that we want to wait for this signal to happen, we will have to lock the lock and then go to sleep waiting for this signal to be sent to us. Once we are signaled, once the signal is sent to us and we've received it, we will wake up and unblock from this call, and we will hold the lock within this critical section until we unlock the lock. Once we unlock the lock, then other threads of execution will be allowed to enter that critical section again. We can send signals to these different threads of execution either one at a time using pthread_conn signal that says do it just for one of the waiting threads that are running right now, and pthread_conn broadcast, which says send it to all the waiting threads that are in this condition variable right now. The key difference between locks and condition variables is very much that we're blocking until an event. Locks will just allow us to enter this critical section if nobody else is running in it right now. Condition variables will always force us to block until someone sends the signal. All right, does that make sense to everybody so far? Okay. This seems kind of weird. This seems kind of weird to even want to do this in the first place. This seems a little strange to want to do this in the first place. I want to motivate this by taking a look at some actual code that uses this for realsies. The code that I'm looking at here is in this directory that's called thrpool in the thread management Git repository. And there are 3 pieces of code in here that we're going to take a look at. The first 2 are thrpool.c and .h. These are 2 files that describe the interface for a thread pool and then the implementation of a thread pool. And then there's this thread madness code that's bad code. It's bad code. To be clear, it's really bad code, but it uses the thread pool as a client. So it's calling all the functions on the thread pool itself. So I'm going to start by taking a look at thr_pool.h. I did not write this code. I want to make that clear. This is not my code. This is code that comes from an example in an Oracle documentation about the use of thread pools. I put a link to the document in the README. I've modified this code to make it compile because it doesn't compile as it's listed on that website. But I wanted to make sure that we all know that this isn't actually my code. The first part of this is we have a constructor. So we have to be able to construct a thread pool. When we're constructing our thread pool, what we're doing is we're initializing things like, these are the minimum number of threads that should be started. So when the thread pool is starting up, you should start up this many threads of execution. And it can spin up more threads of execution if necessary. The ultimate goal of this, I'm going to scroll down to the next part here, is thrpoolq. The ultimate goal of this is I want to be able to give this pool work. I want to say you should run this function in a thread. Here's the function. Please run it in one of the threads that are currently in the pool that you've got. So this min threads here, it's going to call pthread_create that many times initially. And while there are threads that are not doing anything, thread pool q here is going to say, I'm going to take this function pointer, give it to this thread of execution, and then have that thread of execution run that for me. What's nice about this kind of a structure is that we can specify the maximum number of threads. So in the code that we've been writing so far, we've just been putting pthread_create inside a loop, and that kind of says this is how much concurrency we should have at any given time. But if you don't know in advance that you need 10 threads over the entire lifespan of your code, but you only ever want to have 10 threads running at the same time, then a thread pool will help with something like that. The last two functions are kind of similar to what we had with other structures that we've got, but then also pthreads. The thread pool wait function will wait for all of the threads to finish, so it will wait until they're all done, and then once they're all done, we can call the destructor function this destroy. So I'm going to quit this interface, and I'm going to take a look now at thr_pool.c. And I'm going to skip over a lot because a lot of this is not actually super important for what we care about. There's a few different condition variables that we have here. So there's this one that's called busy CV, there's one called work CV, and there's one called wait CV. The one that I actually care to look at for us in this class is this work CV condition variable. This is the one that's going to notify any waiting threads that there is new work for them to do. So let's go down here, and I'm going to go to the create, way down here to worker threads. And what worker thread does on line 176 here is if there's no work in the queue of jobs for this thing to do, it's going to wait for there to be work for it to do. So it doesn't exit, it's just going to suspend itself. It's just going to block until somebody has submitted work for this thing to do. In our thread pool queue function, I'm going to keep going down here to the thread pool queue function. This is the part where we're passing a function pointer, and this line here, 342, says, hey, somebody wake up because there's a new job for you to do in the queue of stuff. So our thread pool queue function is going to add this work, this function pointer to a queue. We're already starting to talk about queues. It's adding it to a queue. And then our pthread const signal is telling any of the threads to wake up and then to start actually working on the function. Once that thread wakes up, I'm going to go back up here to the work function that we had, where we were waiting on this. So that's here. And the way that we're actually calling it is, oh gosh, where is it? There's a place where this is actually calling the function that's being put onto the job. And I think it's here. So there's func that's being passed to this, and then func is getting called somewhere in here. I'm going to quit this, and I'm going to open up threadmadness.c. This is a piece of code that will launch a thread pool. It makes a bunch of work, and then it's going to send work to that thing, and then it's going to clean up after everything's done. So this is an example of using it. The output from this code is expected to be kind of mixed up or messed up each time because we have the same problem with file scope variables, and we're not locking it. Each of the threads are going to run this function. So we're going to have a varying number of differences in output each time we run this. So I'm going to make this one more time. I'm going to make -c, uppercase C in the parent directory. I'm going to go back to deadpool. Oh my God. Deadlock.c, and I'm going to just comment those lines out so that I can compile this code. I'm going to make -c ... I'm going to go back to that. I'm just going to do this, make -c ... and I'm going to say thr_pool thread madness _thread madness. There we go. Okay. So then I'm going to do thread madness, and it's not exciting. It's really not exciting. It's going to just print out this value. It's going to print out something different each time. The point of here is that we're actually using that thread pool for something. So the way that this is ultimately working, and the purpose of this, is that when we're working with this thr_pool.c, it's making a queue of jobs, and it's inserting jobs as they are received into the queue. When there are no entries in the queue, the threads that are in the pool should just wait around and do nothing. When there is work to do, one of them will be woken up and it will lock this queue. It will take the job off of the queue and then it will release the lock so that it does the work that's in the queue itself, or that's in the job itself. This is a very common use case for condition variables. There's a queue of things that you need to operate on, put everyone to sleep until there is something in the queue, wake somebody up to take that thing off of the queue, and then everybody else go back to sleep unless there's more work to do in the queue itself. Yeah.
Is this basically a scheduler done?
Yeah, sort of. Yes, sort of. Is this what a scheduler does? Yes, sort of. The main difference between what a scheduler is doing and what this is doing is that this doesn't know which task or which thread is going to get to go next, but the work is what's decided to go next. So in that sense, like, we're saying this is the function that I want you to call, and this is the order that I want you to call the functions in, but we can't guarantee which thread of execution is going to get that job. The scheduler's job is to decide which thread of execution actually will receive the task that comes off the queue.
How low level schedulers usually?
How?
Are they written in C usually?
Yeah, so scheduling algorithms are generally written in C, but that's distinct from the context switching part and the task switching part. That actual code has to be architecture specific. So like when we were looking at that struct task struct and we saw that thread context part at the very bottom of that very long structure, and all of the implementations were inside that architecture folder, there has to be some code for each architecture that says this is the register set and this is how you should change the values on the register set, and that might be an assembly language. But the act of picking which job gets to go next, we're looking at structures here. So this is an abstraction over this unit of work or unit of concurrency.
Wait, so Apple Silicon essentially had to rewrite everything?
They had to rewrite their context switching and dispatching of threads, but their actual scheduler they would have just been able to keep using because it will have been written in C. They had to recompile it, but they would just be able to keep using it, assuming there are no bugs. But yes, yeah. All right, okay, so that's pretty much it for condition variables that I want to look at. Their main use case, again, is we've got this queue of work or list of work or work that we want someone to wake up and do, and we want threads of execution to stop until that work is available. So at this point, you should be able to identify code that protects a critical section. This was something that we did last class, and you should be able to propose solutions that would avoid and or prevent said deadlock. So in the case that we were looking at today, you should be able to show that doing something like sorting on these accounts will enforce total ordering, and that will break one of the conditions for deadlock that we have. The other thing that you should be able to do at this point is to use condition variables in a program. So acquire a lock, wait on the condition variable, send signals using pthreadconn signal or pthreadconn broadcast. That's it for today. I hope that you all have a great rest of your day, a good weekend, and I will see you all on Monday. Bye, everyone.